Next, let us discuss about the fundamental postulates of statistical mechanics. So while applying this statistical mechanics to gases, some of these postulates are made. So let us go one by one. So number one that we have, okay, so that any gas under consideration may be considered to be composed of a large number of molecules which are constantly in motion and behave like very small elastic spheres. Okay, so the second postulate, we can all the cells in the phase space are of equal size. So in the earlier slides we have talked about the phase space and then some of the small the divisions that we have made to the phase space. So we have seen those phase space. Okay, so each of them are of equal size. Okay, so then all accessible and the phase points lie within this phase space, the phase cell. Okay, so the all accessible microstates corresponding to the possible macrostates are equally probable. Now this we have discussed under the principle of equal a prior probability, where we say that each of the microstates of a system is equally probable, and that forms, as I told you earlier as well, that this forms a fundamental basis for this statistical mechanics. So basically what we can say that if we have a system, okay, so the probability of a macro state of a system is decided or the dependent on the number of microstates of that system for that particular macro state. Okay, or you can think about the thermodynamic probability. Okay, now for system to possess a energy, let's say E, will be decided by the corresponding microstate of the system. So W represents thermodynamic probability. Okay, so that's why, so we can write this as P of E will be equal to some constant C, okay, and then WE we can have. Okay, so in many cases you may see this representation for thermodynamic probability as omega as well, which we had talked about in the earlier videos as well. Okay, so you can, so here I am using WE. Okay, so let's go to next point. So the next is equilibrium state of a gas corresponds to the macro state of maximum probability. So this also we have discussed in the earlier videos as well, where we have said that so the most probable state is that state which has got higher or the most number of microstate, and then we have seen that system will be, or the system will take up that macrostate in equilibrium state. Okay, so basically system will be in equilibrium state by and it will be present in that macro state which is most probable. Okay, is one and the same thing. And then total number of molecules is constant. Basically this is the conservation of matter. Okay, so if you think about, let's say so see, the phase space is divided into many cells. Okay, which as we go along you will see that these cells we can, like, you know, it's a representative of the energy state of a system that we will think about. Okay, let's say in the cell number one there are n1 particles. Similarly in cell number 2, let's say there are n2 particles. Similarly we can have how many ever cell we want. So cell K we have, let's say there are k number of cells in the phase space and nk. So the total number of the particle will be given by n1 plus n2 all the way, it will go till nk, and let's say the total number of particle is n. Okay, so similarly, so basically, so this number is constant. Okay, so and then when, because it's a dynamic system, so the number of this n1 n2 if corresponding to cell number 1 may keep on varying depending upon the situation or the exploration of the system for various microstate or macrostate. Okay, so total number of so total energy, the point number 6, total energy of the system is constant. Of course this has to be conservation of energy. So let's say cell 1 has got, so these cells are of phase space. Okay, so the n1 in cell number 1, so n1 number of particles are there in cell number 1. Let's say that corresponding energy of the cell is E1. Okay, similarly cell 2 is E3. Similarly we can have ek is the energy corresponding to cell k. So the total energy of the system can be written as, so because n1 particles, each of them will have E1 energy, so E1 plus n2 E2 all the way going to nk ek, and this is total energy of the system, which is constant. Okay, so then let us talk about ensemble. Okay, so basically what happens, so as we have seen that if we think about a gas, the simplest gas, okay, monatomic gas, 1 mole of gas you take, and already we have discussed in our introductory videos as well. If you have 1 mole of gas, it will have 10 to the power 23 in order of 10 to the power 23 particles. Imagine how many ways to distribute in various energy states. So there it will lead to a huge number of microstates. Okay. Now, if you do any macroscopic measurement of two gases, let's say, okay, two different gases which are kept under similar macroscopic conditions, okay, so by so the macroscopic condition is same, okay. So if we do the measurement, it's really hard to distinguish between, basically these two gases will represent two representative point in the phase space, okay. Okay, so which one is giving what result, it's very hard to meaning understand from the microscopic point of view. Okay, so basically when you talk about a general macroscopic conditions, because there are many ways to distribute these many particles, so there are a lot of microstate I am talking about. Okay, so when I say a similar macroscopic condition or a macrostate, I deal with not only a, you can relate or extend an idea to not one system, actually a collection of huge collection of system, a pretty large number. Okay, so that's why to deal with this kind of situation gives us introduced the concept of ensemble. So ensemble represents what actually, so it's a collection of a large number of system which are macroscopically, so basically what happens, so this is a large collection of objects. Okay, so large collection of system, okay, which are macroscopically identical. Macroscopically identical. Macroscopically same meaning. In what sense? Its volume, let's say volume, its energy, temperature, number of particles you can think about, okay, pressure, all these things, these are macroscopic properties of the system. These are same across all the systems. Okay, so these systems which I am talking, large collection of systems, these are actually essentially independent, and these are independent systems. Okay, so ensemble means what? To deals with, you know, such a huge number of systems. So that's why scientists gives have introduced this ensemble. So ensemble means a large collection of essentially independent systems which are macroscopically identical. Okay, so if you think about that, now the gamma space will come into play. Okay, so we have already talked about the gamma space. So in the gamma space, because we all know that this is 6-dimensional space, so this is 6-dimensional space, sorry, so this is 6-dimensional, let's say it's a representative momentum, and this is position, let's say, let me just write r here. Okay, so this, when I say same macroscopic conditions, okay, and then slightly change in the sort of microscopic constituent, or slight change in the microscopic behavior or properties of the system. So in gamma space, what will happen? This ensemble will be represented by a distribution of points. Okay, within certain, it's a cluster of points in the gamma space. So now see, so this is not possible for the mu space, okay, to represent this ensemble. So idea of ensemble help, as we go along, we'll discuss more on that, why it is so helpful. Okay, so to the basic idea here to know about the ensemble is a large collection of very independent systems which are macroscopically similar. Okay, similar in what sense? That I have talked about: volume, energy, temperature, number of particle, pressure, and etc. You can have any other macroscopic properties which are constant, and this ensemble gives a like distribution of points in the gamma space. Okay, so next, depending upon how okay, just let's continue here. So ensemble is a large collection of number of macroscopically identical but essentially independent system, which I have talked about in detail. Okay, now depending upon the various interactions that we have, that gives us given the standard or the standard way of meaning having different kinds of ensemble, defining different kinds of ensemble. So we have three of them, so we'll go one by one. Okay, so we can talk about first one is microcanonical ensemble. Canonical ensemble. Second one is canonical ensemble. Third one is grand canonical ensemble. Grand. Okay, so now let's go one by one. Okay, so in microcanonical ensemble, what happens actually, the different all, so say the ensemble means what now? A large collection of systems. Okay, listen to the independent system. So each of them, one thing you have to remember, macroscopically each of them are similar. Okay, so what all macroscopic properties are same in this under the microcanonical ensemble, you can think about it has got same energy. Okay, so it has got same volume and it has got same number of particles in the system. Okay, so typically it is represented like this. Okay, so let's say I have let's say I have one system. I can make a copy of this system. Okay, copy. So let me just do this first. Okay, I'll just try to make a nine of them. Okay, so then let's just arrange them in particular a particular order. Okay, so each of these, the box you are seeing, it's representing one system. Okay, so and then for all this system that we are seeing here, so it has got same energy. Okay, so it has got same, each of them can be represented, so macroscopically they are EVN represented by each of them. Okay, and I can think about all of them are placed, let's say there is some surrounding to that. Okay, and this since these are at the same, all of them, all the system, let's say I can name them with let's just 1 2 3 4 5 6 7 8 9 of these 9 systems. These are representative of a large collection of system. So each of them has got same energy E, volume same V, number of particles same V. Okay, so so there cannot be any exchange of particles among these systems. So that's why the system wall is, or these are made up of, like, you can think about impermeable walls, impermeable, so, and they are isolated, right? So they are, because no energy can be exchanged, and the walls are rigid, their volume is constant. Okay, so they are well separated and isolated. Okay, there. So in this case, what happens, all the systems are of same energy, volume and number of particles. So there is no exchange of particles within the system. So the wall or the wall governing the system is impermeable. They are well separated and they are rigid. Whereas in canonical ensemble. Okay, so all the systems are, so let me just, I hope I can make again some copy of all these things. Okay, so basically just, I think it will be enough for me. Okay, so here what I will do, all the systems are brought, or they are brought close, I mean they are separated by okay, so they are diathermic wall, meaning the, and then all of the systems are put in some kind of heat reservoir. Okay, okay, so all of them are put in some kind of, let's say it's a heat reservoir. Okay, so the entire so it's a heat reservoir, and they, let's say, maintained at temperature T. And okay, and within the system 1 2 3 4, so it has got same temperature, so the walls of the systems are diathermic, meaning the diathermic energy can exchange among these systems, and wall is rigid, volume cannot change, and the same number of particles, again still the walls are impermeable. Okay, so this, so here seen earlier microcanonical energy was constant. Okay, but here that thing is relaxed, so the entire systems are placed in a heat reservoir, or in connected to a heat reservoir. So the temperature is maintained to let's say temperature T for all the systems, and the volume and the number of particles are meaning same what for each one of them. So they are made up of rigid and impermeable walls. Okay, and for the grand canonical ensemble, so it has got same temperature T. Okay, so and this, so you can think about the system. Okay, the small system that we have within. So now what I have to draw, so I'll just draw probably 1 or 2 systems. Okay, think about this one system, and other is, let's say, sorry, it's getting connected. Okay, so why am I drawing dashed lines? Because I am trying to represent that the walls are permeable, so the it can exchange the number of particles. So the system in the grand canonical ensemble, what happens, it has got same temperature, meaning all the systems are interconnected, or that they are thermally connected. Okay, they are maintained at same temperature, and all of them are put in a heat reservoir to maintain the temperature T, and the rigid walls. Okay, so volume is maintained V, and they are at same chemical potential. Okay, and where, you know, the to maintain the same chemical potential, what will happen, there is a number of particles, the exchange of particles between or among these systems are allowed. So basically what happens in the microcanonical, the energy and matter was not allowed to exchange, whereas in the canonical energy was allowed to exchange, and whereas in grand canonical ensemble both energy and matter are allowed to exchange. Okay, both energy and matter are allowed to exchange. Okay, so depending upon the situation, we shall take up the problem following, meaning the whichever ensemble is suitable to carry out the which to the experiment, or to apply the theory of statistical mechanics.